Hey everybody, welcome back to Quarantine Physics. I had a few requests for you guys to meet my dog. So this is Sam, she's our new physics mascot. And today we're going to be talking about simple circuits, circuit diagrams, and circuit components. All right, everybody. So we're going to continue our discussion of electric circuits now. Last lesson we talked about electric current. We moved away from our study of electrostatics. Now these charges are free to move around as long as there's what we talked about last. Get started. All right, everybody. Today we're going to start our discussion about electric circuits. Last lesson we talked about electric current. Now these charges, in electrostatics, they start charged were stationary, but now these charges can move from one place to another under certain conditions. We're going to start discussing circuits, and we're going to put these charges to work for us. By setting up circuits, we can make these moving charges do things like light up our homes, charge your cell phone, things like that. So we're going to talk about circuit basics. We're going to review current a little bit, and we'll dive in and get started. I really wanted, if I'm being honest with you, I really wanted to run out and get electric stuff that I could, show you on the camera. But I figured it's probably not a good idea to go out and buy anything right now. So I'm going to do a lot of showing you stuff on the screen, hand waving. Hopefully when we're back in class, I could show you some of these things live. But here are simple circuits. My high-tech switcher here. Okay, so let's just review current a little bit from last lesson. We said current flows from a place of high potential to a place of low potential as long as there's a connection between those 2 points. At the very end of the lesson, I said that we talk about conventional current flowing from high potential to low potential. We know that's not truly the direction that charges are going in. Electrons are what's moving. Conventional current is defined of where a positive charge would move, if we can let it move, but electrons are truly flowing in the opposite direction. But we track the flow of conventional current through a circuit. It's the flow of positive charge from a place of high potential to a place of low potential. It's the opposite of the actual electron flow. Okay, so like I said, 2 different places of different potential. Let's say I have 50 volts up here. 25 volts down here, there's a connection. The conventional current will flow from the 50 volts to the 25 volts. Okay. Now, what's really interesting about circuits is the charges inside of the circuit move really slowly. So when you flip the switch in your house and the lights immediately come on, how could that be? If the charges really do move slowly in a circuit, why do things happen instantaneously? Well, charges in a circuit, believe it or not, move less than a millimeter per second. Those electrons are really not moving quickly at all. But when you flip the switch, there's now an electric field to move those charges around. Those charges are packed inside of the circuit. There's a charge everywhere inside of the circuit. And as soon as you flip the switch, all of those charges start moving together. And because those charges instantaneously almost, the electric field moves about the speed of light. That's how fast the signal moves. As soon as you flip the switch, the electric field goes on and all those charges start moving. They move very slowly, but they do start moving throughout the circuit. Okay. When we talk about electric currents, we're not talking about the speed at which the charges are moving. We're counting how many charges are passing a specific point every second. Okay. So how does current actually flow? Like I said before, a conductor has to be part of a closed circuit. We need a closed loop of conductor in order for the current to flow. And we need a potential difference between 2 points. So we need a place of high potential, a place of low potential, a connection, and then current can start to flow. That's the basics of electric circuits. And by better understanding these basics and how they work, we can start talking about more complex connections of putting all these kind of components together and making them do stuff for us. Okay. So let's get these charges moving. Let's actually put them to work for us. Here's a case of what we call a simple circuit. What we have here is a voltage source. This voltage source is the source of our potential difference between these 2 points. This is actually what allows the charge to start moving around this current, our voltage source. Now notice that there's a closed loop of conducting wires. If this wasn't a closed loop, if we disconnect one of these wires, then current cannot flow and those charges can't do any kind of work. This light won't light up. So we have a closed loop of conducting wire, a voltage source to pump those charges along. We have the thing we're trying to power. We call that usually an electric load if you look up any kind of like electronics or electrical engineering. Our goal here is to light up this light bulb, right? So this is our load or our resistor because it resists the flow of current. And here we have our electric switch. Now, just like the switch in your light in your house, if we flip this switch, we could break the current. Now it's not a closed loop anymore and the charge won't flow. Switch is a nice, easy way for us to either have the whole circuit put together or to easily break the circuit to stop the charges from flowing. This is a simple case of a circuit. The first thing I want to talk about is this voltage source and what that means and where that electrical pump really comes from. Okay. The most common type of voltage sources that you guys are probably used to is our batteries, right? Here's an example of all different types of batteries that you might have seen. We have our AAA, AA, C, D, 9 volt. Like I said before, a battery acts as an electrical pump pushing the charges around the circuit. When you have a circuit constructed, those charges are packed inside of the circuit, but there's no reason for them to move unless there's a potential difference between 2 points. A battery provides that potential difference for us, that voltage. There's a different potential from the positive terminal of the battery to the negative terminal of the battery. Provides a constant potential difference between its terminals. That's what allows those charges to move around in a current, in a circuit. And how do batteries work? Well, they convert chemical energy to electrical energy. There's a chemical reaction that occurs in all of these batteries. And because of that chemical reaction, there's a voltage between these 2 terminals and charge is allowed to move through our circuit. Okay. All batteries provide a cause a direct steady current throughout the circuit because it's a constant potential difference between the terminals. So those charges will move directly from one place to another, back into the battery, all the way around our circuit. Batteries provide direct current. The type of circuits that we're going to be discussing in this class are DC circuits, direct current circuits. Those charges will be moving around only in one direction. You might have heard of AC circuits as well. I'll briefly discuss what AC circuits are, but AC circuits are a little beyond the scope of this course. If you have any questions about AC circuits though, let me know. Batteries provide DC current, like DC circuits, direct current circuits, where the outlets in your wall provide alternating current. That's AC circuits. And what AC circuits do frozen. There we go. Okay, so notice a battery pushes these charges along only in a single direction. The charges move slowly, but they're all moving together. What this diagram is showing you is how conventional current would flow. The conventional current flows around this direction in the circuit. The electrons are truly moving this way, but we track conventional current in circuits, which is the direction positive charges would flow if they were flowing. Notice they move around in a steady direction. That's DC current. AC current, it actually wiggles the charges back and forth, which sends an electrical wave through our circuit. And AC current could power things as well, but we need DC current to do things like charge our cell phones because we need that charge to flow steadily in one direction. AC current is just easier to send over long distances, and that's why we have AC current coming out of our wall because it's coming from a power plant really, really far away. Side story, you might have heard of the band AC/DC. AC/DC literally got their name because they were looking at a laundry machine, and they looked at the power supply of their laundry machine, and what the power supply does is it converts AC current, it converts AC to DC. So they looked at that, it was AC/DC, and that's how they got the name for their band. But when you plug in your cell phone into the wall, it converts the AC coming out of the wall, the alternating current, to direct current so that those charges can steadily flow to your cell phone. That's why there's a big box in any kind of cell phone charger. That's what does the conversion for us. Okay, let's get back to it. Real quick, before we move on to the next thing, I want to talk about these batteries real quick. You've seen these batteries, you put these batteries in your devices, but what do they actually do? What's the electrical properties of these batteries? Well, AA, AAA, C, and D batteries, they all provide a constant potential difference of 1.5 volts. Every single one of them. All of these are 1.5 volt batteries, except for our 9 volt battery, which, you guessed it, supplies a constant steady voltage of 9 volts. So then what's the difference between all these batteries, right? Why do I have to use a D battery sometimes instead of a AAA if it's always providing the same potential difference, the same voltage? Well, D batteries can supply more current than AAA batteries because of the size. That's why in flashlights, where we need really bright flashlights supplying a lot of current, we will tend to use these bigger D cell batteries. But in tinier electronics, like your calculator that doesn't need as much current, we can use AAA batteries. Okay. So, we understand circuits. We know we're pushing those charges along to do work for us, right? Because those charges can convert that electrical energy inside of the circuit to light energy for our lights or whatever we're trying to power. But what do we actually hook up inside of the circuits? How can we actually build these circuits to make them work? Here's an example of what we call a schematic circuit diagram. These diagrams take what are complicated circuits with all kinds of different wires and components and tries to simplify it as much as possible so we can easily read it and build that circuit ourselves somewhere else. This looks complicated. And this is beyond what you guys need to know for schematic circuit diagrams, but I kind of wanted to show you what one looks like. This is a schematic for an intruder alarm, actually, believe it or not. This little switch would close when, let's say, you open a door or something like that, right? The switch will go off, and then the buzzer goes off, letting you know that someone opened your doors in your house. Okay. Like I said, this is complicated. We're going to break it down and really understand what's going on with each one of these components inside of the circuit. All right. So something that you will be expected to know how to do is how to draw these circuit diagrams and read these circuit diagrams so we can know what they mean. We had this simple circuit that I showed you before. We have a voltage source, our load, which is our light that we're trying to turn on, and our switch. This is what the circuit would look like in real life with all these conducting wires and all these connections. But we can simplify this so we don't have to draw it out each time with our schematic diagram. We're going to talk about what each one of these mean. This here is our battery. This is our voltage source. This is the symbol we use for our battery. Here is our switch, right? Because the switch could be open, not allowing current to flow, or closed. And here is our lamp. This is a nice simplified diagram for us so we can easily communicate what's going on with these circuit diagrams. All right. What I'm going to do for the next little bit of this lesson is I want to go through each one of these circuit symbols. These are the circuit symbols that you will be responsible for. You don't have to memorize these because this is in your reference table on page 4. So if you ever see a circuit diagram and you need to refer to what each one of those symbols might mean, open up your reference table, go to page 4, and you will see this table for you. Let's go through each of these, what they mean and what they do for our circuits, and then we're going to try to build our very first circuit diagram. Okay. So the very first thing, these two here, are the cell and the battery. Okay, so in our circuit, the cell or the battery, the voltage source for our direct current, our DC circuit, looks like this. Technically, a battery is a grouping of cells. That's where that term battery comes from. If you break down the word battery, it literally means grouping. So when you have a grouping of cells, you have a battery. For you guys, for Regents physics, these tend to be used interchangeably. They're just simply a voltage source of our circuit. When you have a battery or if you have a voltage source, this is what it's going to look like inside of your circuit. The reason why I put this diagram here is because in a lab environment, this tends to be what our voltage source is. You can set whatever constant voltage you want with this little knob, and then you hook up the wires to these two terminals, and that would supply a steady DC current to our circuit, direct current to our circuit. So that's your cell and battery, your voltage source. This is good. This is just like class. Everything's freezing on us. There we go. Next. The next thing on our list is the switch. Now, switches are useful because when you have a circuit, your goal is to get something working, but we don't always want that thing working, right? We don't always want the lights on, so we could put switches inside of the circuit. Switch is an easy way for us to allow current to flow or to not flow, whether we want the thing to work or not. When you have an open switch, the terminology is open switch. Then when the switch is open, the circuit is off. So this here is showing you an open switch, as well as this showing you an open switch. The circuit is off and it breaks the path of current flow. If you don't have a closed loop of wire, you can't have current flowing. And we call that an open switch. If we close the switch, the circuit is on, and then current is allowed to flow through our circuit, because now we have an unbroken path of conductors. If I take this metal and I close it here, now we have a closed loop of conductor, and now that current is free to flow. Okay, so the next thing on our list in the reference table is a voltmeter. A voltmeter, just like it looks like, is a device which measures voltage. It's a meter for volts. It measures the potential difference between 2 points in a circuit. So what we do is we take our voltmeter and we actually take the two little leads and we put them on each end of the component that we're interested in, right? So I have my voltmeter, I'm looking at my lamp, I could put the two little ends here, and then now we could see the potential difference, the voltage, the difference between this point and this point. And we can see what the voltage is across this component. Now notice here, we're creating a whole new branch in the circuit for our voltage, but checking what the voltage is between these 2 points. So voltmeters must be connected in parallel around the points. And like I said, that means it creates a whole new branch inside of the circuit. If we had a voltmeter like this one, like that you might see in a physics lab, you take two of the ends, right? You have wires connected here, we touch them to each side, and it'll tell you what the voltage is between those 2 points. The potential difference between those two locations in the circuit. Okay, so a voltmeter measures voltage. An ammeter measures current, measures amperage in a circuit. So an ammeter is a device which measures current, and it must be connected in series, which means it's just connected directly in the pathway of our components. So where a voltmeter was in parallel, making a whole new branch, an ammeter is connected in series. We're going to talk about those terms a little bit more, series and parallel, when we get into more complex circuits. But all three of these components are connected in series, which means if we track the currents going through the circuit, it flows through each one after the other. And that's the direction at which current flows. It flows out of the positive terminal of the battery, this longer line. This is a cell here. The current flows through the ammeter, and then it flows through our lamp. And this ammeter will tell us exactly how much current is flowing. It literally looks and sees how many charges are passing every second, just like we defined last lesson. So you can hook up the ammeter to the circuit and see how much current is flowing. Next is a resistor. A resistor, quite literally, resists the flow of current. It's a component which resists the flow of current, and resistors are used to ensure that the correct electrical specifications, voltage and current, are delivered to each portion of the circuit. So we put a resistor in to slow down the flow of current. Here's what resistors might look like if you saw them in a lab. They have these colored bands, which there's a code to figure out how much resistance each one has based on these colored bands. And we're going to be talking about how to actually quantify resistance in the future. But all you need to know right now is they resist the flow of current, slows down the current flow. And here's the symbol that we use in our circuit schematics. Okay. Now these resistors have a constant resistance. It doesn't change. But there are also variable resistors. A variable resistor, by turning this knob, we can actually change the resistance of that section of the circuit. Variable resistors have this symbol, and variable resistors are sometimes called potentiometers. Okay. And the last component that we're going to talk about is the lamp. For Regents physics, in general, the load, the goal of building a circuit is by lighting up a lamp. If you go deeper into your study of electronics, there are other reasons why we hook up a circuit. But for now, a most common load that you'll see is the lamp. Converts electrical energy to light energy, and lamps also resist the flow of electricity, so they can act like resistors inside of our circuit. Here's what a lamp looks like, and there's our schematic diagram, schematic symbol. Okay, so that was a lot, but what I want to do right now is I want to build our very first circuit. We're going to build our first circuit schematic based on the given information here, and we'll walk through it all together to see how we could set this circuit up. We want to draw a circuit which consists of a lamp, a cell, an ammeter to measure current, and a voltmeter to measure the potential difference across the lamp. Here are the components we need to use, but I didn't have to give you this because you could just look at page 4 of your reference table to figure out what those symbols are. We're going to move over to the whiteboard and build this circuit all together. All right, we're at the whiteboard. We're going to draw our first circuit based on the specifications that were given in the last slide. We want a lamp, a cell, an ammeter to measure the current, and a voltmeter to measure the potential difference across the lamp. Again, we build circuits to do things for us. We want to use this electrical phenomenon to our advantage. So if I gave you each one of these components, how would you set up the circuit? Okay, so here's what I recommend when drawing circuits. Always start with your cell or your battery. Now, technically they said cell, and if you look at your reference table, that's our cell. If you want a battery, you just kind of put a few cells together. But either way, it's our voltage source for our circuit. That's what's actually going to pump the charges along our circuit. Okay, so we need to make sure we hook up our circuit to a lamp. We can do that with conducting wires. Circuit schematics tend to be very boxy. Anytime you see a straight line like this, this is a wire inside of our circuit. So now we have wires hooked up to our cell. No current is going to flow in this circuit because we don't have a closed loop of a conductor. We have a voltage source, but we don't have a closed circuit. We need there to be a lamp in this circuit. Look at the reference table. It's a circle with some squiggles in there. There you go. That's our lamp. Our lamp lights things up. It also, you see the lamp lighting up, but what you don't see is it also resists the flow of current inside of our circuit. If we didn't have a lamp or a resistor inside of the circuit, and we just hooked up our battery to some wires, that's actually called a short circuit because there's not enough resistance. That current flows like crazy, and that's how you actually end up with fires and things like that. We don't want any kind of short circuits in our circuit. We want there to be resistor. We want something to resist the flow of charge. Okay, we want an ammeter to measure the current. Ammeters need to be hooked up in series, so it has to be in the path of our current flow. So an ammeter can go right here. Boom. All right, now we have a closed circuit. If we set up this circuit, it will work. We have our voltage source. That provides a potential difference between these 2 points. Let's say we had like a 9-volt battery. That means there's 9 volts of potential difference between this point and this point. And because there's a potential difference between these 2 points, charges can now flow through our circuit because they want to flow from a point of high potential all the way around to a point of low potential. Okay. Not only that, but as the current flows, you can always track the flow of the current. It'll go through our light, turning it on, and it'll flow through our ammeter. So we'll actually get a reading on our ammeter. We'll know how much current is flowing through this circuit. But not only that, we need one more thing. We need a voltmeter to measure the potential difference across the lamp between the 2 different points. So I want the potential difference from here to here. There will be a difference in potential in these 2 points. There will be a voltage across this lamp. And we'll understand why in a future lesson. But for now, we just want to set up our circuit. We could put a voltmeter right here. Voltmeters need to look at these 2 different points. We'll try a little smaller. Make it a mess over here. Go. Voltmeters need to look at the 2 different points in the circuit to measure the potential difference. So we have to hook it up in parallel. There we go. Creating a whole new branch of the circuit. I like to think that the voltmeter needs to look here and it needs to look here and see what the potential difference is between those 2 points. So we set up a voltmeter in parallel, and now we can see what the voltage is between those 2 points. If I hooked up the voltmeter here across the battery, we would see that there's a potential difference of 9 volts across the battery because the 9-volt battery supplies a voltage from this end to this end of 9 volts. That's the whole point because it pumps the charge along inside of the circuit. And that's it. We drew a circuit with a lamp, a cell, there's a voltage source, an ammeter to measure the current, and a voltmeter to measure the voltage. Okay, now something I want you to think of though, is this the only way that we could have hooked up our components, or is this the only way that we could have drawn this? As long as you follow the rules. Yeah, ready? As long as you follow the rules, you can put It's dying on me. Let's try this one. As long as you follow the rules, I can put the cell here. I could put the ammeter here. And I could put the lamp over here. Okay? And we could put the voltmeter here. Is this a valid way as well? Well, we have our cell, which is our source of voltage, our potential difference, right? Current is flowing in series through the ammeter and through the lamp. This is fine. This is a valid way to draw it. And we're measuring the potential difference across the lamp. There is more than one right answer here. So what I would always say is start with the cell or the battery, Make sure you follow all the rules for our components. Ammeters need to be hooked up in series. We got to run from one component to another. And voltmeters need to be hooked up in parallel across the component of interest. All right, and that's it. We're going to keep exploring this idea of circuits. Could be a little tricky, but as we really work through the concepts, hopefully it'll start making more and more sense to you. Hope everyone's doing well. Hope you're all staying safe. Feel free to reach out anytime with physics questions, or if you just want to chat. I'm always around here for you guys. All right. Hope everyone's doing well.